Syzygy, episode 18, The Mysterious Planet 9. And welcome back to Syzygy, episode 18. It's been a while. We've been away. If you're an avid fan of Syzygy, you might have noticed that there was a bit of a pause somewhere between, I don't know, early August and mid-October. We went away on summer holidays, northern summer holidays. And that's okay, isn't it? We're allowed to have a bit of a break. But joining me back from her extended summer séjour overseas, she's been gallivanting around all over the place. Emily Brunsden, welcome back.
Hello, hello.
Emily, what have you been doing? Where have you been?
Well,
Where haven't you been?
Yeah, I've been on my Euro tour, Euro Tour 2018.
Fantastic.
Which involved a suite of conferences, meeting a bunch of other astronomers.
Oh, there were conferences, were they?
Oh, it was really hard work.
Look, I saw your Instagram posts and I didn't see a lot of conference activity going on. I saw a lot of selfies in really beautiful places, but I don't remember seeing.
That may have
I
happened.
don't know. I don't remember seeing slides and a lot of people sort of scratching their chins going, yes, very interesting conference material. No, I saw beautiful things in lovely places.
But how often do you really take a selfie of yourself watching a presentation at a conference?
Look, for those of us who are left behind not in beautiful places, I think that would have been the right thing to do. I'm just saying. Right?
Well, you're just a grump then, aren't you?
Yeah, well, fair enough. So welcome back, and welcome back to, if we did have seasons in Syzygy, which we don't, but if we did, this might be season 2.
Yeah.
In this episode, we've got some pretty exciting stuff to talk about. We're talking about the farthest reaches of the solar system as we know it. And in particular, there's been a brand new dwarfy planety thing, and we can talk about those technical definitions shortly, but a little thing called the Goblin, which I think's quite fun. It's been discovered way out there in the solar system. But it's not just the discovery of this that's interesting. It's what it points to. It suggests maybe that there might be something else even more interesting out there. Emily, take us through this. What are we talking about? What's the Goblin and what's its secret?
Well, isn't it brilliant that we're talking about the Goblin in October when it's all spooky and Halloween-y? And then there's this other thing out there that it's pointed towards that we also can't see, but it's mysterious. We don't really know what it is.
Can I just say, the Goblin, and it's a dwarf planet, this is beginning to sound like some kind of weird Dungeons and Dragons game. This is astronomy. Can we please get our feet back on the ground? Why is it called the Goblin?
Well, its proper name is 2015 TG387.
Right. It needed a better name.
We could go with that. But
does the Goblin come from the TG part?
It does.
Right. Okay. So in its name is TG, the Goblin. It's Halloween time.
And it was Halloween time in 2015 when it was discovered.
Okay. All right. With you. So the Goblin is a dwarf planet. And where? Why? How? Why do we care?
Yeah, well, it's somewhere in between kind of this trans-Neptunian object, which we'll talk about what that definition means, and a dwarf planet. It's just a little wee thing. It's about 300 kilometres across.
So that's small.
That's really
tiny.
little.
Okay.
Yeah.
So lump of rock flungen around out in space. And that's a real word, by the way, flungen.
Yep.
I just threw that one in there. It's a technical astronomical word. Lump of rock out there in space doing its thing. Where is it?
On an absolutely crazy orbit around our sun.
Yeah, I was reading about this. It's nuts, isn't it?
It's really, really
nuts,
weird.
Nuts in the sense of it's a really big orbit. Like it goes on a really long way.
Really, really long way. So well beyond the orbit of Pluto is the closest it comes. And then it goes something like 60 times further than that, way, way out onto the far-flung reaches of the solar system.
Bonkers. So we're going to have to scaffold this a bit. We're going to have to sort of figure out size scales, because when you start thinking about the solar system, you very quickly run out of intuition, I find. But before we do, so what is the big deal about the Goblin, though? We found it, but we found lots of lumps of rock in space before. So why was this one in the news? What's newsworthy about the Goblin other than its seasonally appropriate name?
So if you notice, it's 2018, right?
Yep.
We could have announced we found this thing in 2015.
Yeah, 3 years ago. Why have they been waiting so long?
So we got an orbit calculated from it, and from that orbit, we can work out that actually its orbit's not quite what you might expect it to be.
Ooh.
It seems to be getting a little bit of tugging of gravity, or it's needed to have been perturbed a little bit from the gravity of something else.
Of course, we understand orbits pretty well. If you look at a lump of rock going around the sun with a bunch of other planets that we know about, then you can do those calculations. Some of them can get a little bit curly, but you can calculate what that orbit should be really, really well. We're good at that in astronomy, and I'm counting myself in amongst you, Emily. I'm including myself in that group. We are good at that. And so when you see an anomaly, when you see it's not quite what we expect, what does that tell you?
Yeah, and there's a group of these objects now, and they're all starting to point towards the same thing, which is very, very exciting. And that's that there might be another planet in our solar system.
Ooh, another planet.
Another proper planet.
An actual, real, honest-to-goodness, no mucking around, this is a planety planet. And it would have to be an actual planety planet because it's got to be pretty big, right?
Yeah, so this is looking at something out there that's maybe a few times the mass of the Earth, maybe tens of times of the mass of the Earth, a super Earth. And
so not sort of Jupiter and Saturn sized, but not tiny either. This is not a Mercury or a Pluto. This is big.
It's pretty big. And it's got to be big enough to have this kind of influence, to have probably changed the orbits of several of these types of objects, like the Goblin.
Now, this is the mysterious Planet 9. Isn't it? Now, I remember going back through time that astronomers used to talk about Planet X, and there was evidence for, way out beyond Neptune and Pluto and beyond the debris that's out there. There must be this mysterious Planet X for reasons, right? When did Planet X become Planet 9? Sorry, why did that happen?
It's interesting, actually, because I think my very first astronomy project when I was a little kid in primary school was looking at a news article about Planet X.
Ooh.
Yeah.
So this is coming full circle here.
A few years ago now. Anyway, this
like
was
6 years ago?
Yeah. Hang on. So back in those days, we had 9 planets in our solar system. We had Pluto. And so we were looking for Planet 10, Planet X. It was kind of Generation X. It was all very, very snazzy. Now, since then, what those measurements were based on, which was based on other kind of objects in the far solar system, that object has not appeared, basically.
Right. So what you're saying is the evidence that was saying, hey, there should be this Planet X, Planet 10 out there somewhere, turns out not so much.
Not so much.
And so the concept of Planet X, okay, we can ignore that now. But now 2 things have happened. We've got new evidence that maybe there's another lump of stuff out there planet-sized. And we've also lost one of the canonical 9. Pluto's been pushed off the edge. We've now got 8 official planets. And so if we've got another one, it must be Planet 9, not Planet X/10. Oh, look, if that's confusing, let's just back up a little bit. Emily, take us through the size of the solar system. Because in order to really grasp the scale of this new, of the Goblin's orbit and where we're looking for this extra planet, Planet 9, we need to sort of get a bit of a sense of where in the solar system we are and where they are. And it's a bit mind-boggling. So take us through this. How can we cope with this?
Well, it turns out that the solar system is a really difficult thing to measure the size of, because where do you say the end of the solar system is? That's a difficult question. We'll go through some of the definitions you might use to define the edges.
Okay.
So if you start with the sun, the sun is the center, then we're going to say we've got 150 million kilometers between the sun and the Earth.
150 million K from the sun to the Earth. Okay.
Yep.
All right.
Now, we're going to change that unit, and we're going to change it from 150 million kilometers, because otherwise we'd just start talking about millions and billions and blah, 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 blah.
And eventually that just becomes...
It's just numbers.
Yeah.
So we're going to call that 1 astronomical unit.
Okay, 1 AU.
Yep.
All right.
So one distance between the Earth and the sun.
Right. So if we think about... So what would be, say, Mars... Right? In astronomical units, Emily's looking at me across the table. Come on, you're an astronomer.
All of the numbers don't fit in my head at the same time. Forget about all the planets. We know what planets are. We go out to Neptune. Neptune's the furthest planet. That's at 30 astronomical units.
Okay, so all of the planets that we consider to be planets, from Mercury out to Neptune, are within 30 astronomical units, within 30 times the average distance of the Earth from the Sun.
Yep.
30 of them. Okay, so that's a number that we can deal with. 30. That's, I could see that. All
and
right.
they're all in the same disk, right? They're all in the same plane. Then we have something called the Kuiper Belt. And the Kuiper Belt runs from about 30 astronomical units, so kind of Neptune, up to 50.
Okay, so we're still within imagining distance. I can picture that in my head.
Yeah.
And tell me about the Kuiper Belt. What is it?
So it's a little bit like the asteroid belt, which sits between Mars and Jupiter.
Right.
Except it's further out, colder, got some icy stuff in it, little lumps of rock. This is the stuff that Pluto hasn't cleared from its orbit, which means it's not allowed to be a planet.
Right. So, and would that have come from sort of similar origins to the asteroid belt between Mars and Jupiter? Would it be sort of leftover detritus from a collision?
Leftover stuff, probably. Maybe it never formed into something. We have some evidence that the asteroid belt might have been a protoplanet at some point, but maybe not quite the case for the Kuiper Belt.
Okay, so we've gone Neptune about 30 AU, and then the Kuiper Belt from 30 to 50. It's around 50 AU. So that's the edge of the solar system?
Not quite.
No?
There's a bit more solar system after that.
Right.
So Pluto itself sits within the Kuiper Belt, right? It's got this weird elliptical orbit. It's not in the same plane as the rest
it's tilted up, isn't it?
Yeah, so it's tilted a bit to everything. It's goes from anything from what's Pluto like 30 to 49-ish. So kind of basically the Kuiper Belt almost defines Pluto's orbit, astronomical units. So yeah, Pluto's a bit eccentric and weird. And then you have a little bit of a kind of a gap, if you like. There's sort of the density of objects decreases. There's not nothingness there, but there's not as much stuff, if you like. And then we reach something which we call the heliopause.
Pause meaning
stop.
Take a break, have a gap.
Yep.
Yeah.
And the heliopause is basically where the end of the sun's radiation influence it stops, basically.
The sun's radiation influence.
Yeah. So let's think about the sun's putting out this thing called the solar wind. It's all the charged particles that are pouring off the sun. And that kind of creates this environment that we live in the solar system. And it's almost like we kind of live in the very, very outer layer of the sun. It's just a very, very low density
it's what
atmosphere.
gives us the auroras, isn't it?
Yeah.
The solar wind. It's all these charged particles coming past and getting caught up in the Earth's magnetic field, which then gets channeled up towards the poles and does all sorts of crazy stuff in the atmosphere and causes these bright lights, which if you're lucky enough to see, is pretty awesome. I look forward to seeing that one day in my life, but I haven't yet. But that's coming from the solar wind.
Yep.
So you're saying that out here at the heliopause, that's pretty much done and dusted by that.
So that's the barrier between where the sun's influence stops and the interstellar medium's influence takes over.
Ah, okay.
So it turns out that the vacuum of empty space is not very vacuumy.
Not
and
so empty.
Not really empty at all.
Right, okay.
So we have the interstellar medium, so the space between stars is actually full of lots of gas and dust and that sort of stuff. So this is kind of the boundary between the sun's very, very outer atmosphere, if you like, and the interstellar space.
Right. Okay, so that's the heliopause.
Yeah.
And that's out how far? How far
So
away?
we're looking at maybe 120-ish astronomical units.
Okay.
It's dynamic. It's not a static thing. It changes as the sun's magnetic fields change, as the sun's solar cycle changes, and it changes which direction you're looking at. So the sun's traveling in a direction around the galaxy. So it actually pushes, it's got a little bow shock kind of in front of it as it's plowing into this interstellar medium. It's like if you're trying to push one blob of oil into water or something like that, then you've got two different types of material that you're pushing against each other.
Right. So the sun's sort of leaving as you called it a second ago, like a bow shock. It's leaving like a wake behind it, like a boat going through water in a sense. And so if you're looking at the sun from one side, then the heliopause is going to be a little bit in a different place to looking at it from the other side.
Yeah.
Just because of the direction it's going through the interstellar medium. Is that what you mean?
I think one description I saw that was quite good is that we kind of have a tail going behind us.
Yeah.
So the heliopause or the influence of the sun sort of drags along a bit behind us, and it's kind of bunched up at the front, if you like, in the direction
so
of travel.
that's sort of 100, 150
to
astronomical
the
units
closest
out.
sort of edge of that.
Yeah.
And we know that actually pretty well because we had Voyager 1, which actually reached the heliopause in 2012. And what we noticed was that there was a really sudden drop in the density of the plasma and the density of material that Voyager 1 was travelling through.
Now, this is Voyager 1, so there were 2 Voyagers, weren't there?
Yep.
Sent out, they explored the solar system and then just kept on going.
And going.
Remind me, when were they launched?
In the 70s.
In the
77,
70s.
yeah, 77
and they're
was
still going.
Yeah.
Are we still in touch with them? Do we still
Yes,
get...
yep, we still receive information from them.
I just find that staggering.
Yeah.
These
It's
are the ones.
so cool, yeah.
These are the ones that have got the special, records on them with
Yep.
information about we Earthlings and our planet and stuff, and little charts showing human beings and where we are in the solar system and all of that. And it's flinging off into interstellar space eventually, I guess. And you're saying in 2012 it reached the heliopause.
Yeah, so Voyager 1 became the very first man-made object to leave the solar system.
Goodness, and that's 5-6 years ago.
Yeah. But we didn't just send one Voyager. We flung Voyager 1 off in one direction and we thought, well, let's send off Voyager 2 in a completely other direction. I mean, it's really cool. It's just kind of, let's just throw it out there and see what happens, right?
I just find it staggering that we're still in touch with them.
Yeah.
I think that's brilliant.
Yeah. So actually, on October 5th, then NASA have announced that they think that Voyager 2 might be about to leave the solar system as well.
Cool. As in at that same point, at the heliopause.
Yeah, at the heliopause.
Right.
So basically, they're seeing a pattern in the number of cosmic rays that Voyager 2 is receiving that was the same as the pattern of cosmic rays that Voyager 1 had about 3 months before Voyager 1 left the solar system.
So crossing over that boundary.
Yeah, so they think it might happen to Voyager 2 very, very soon.
Very exciting. Go little Voyagers.
And it'll be the second object that we've ever left our solar system.
Now it's a race. A race.
Yeah.
So, okay, that's the heliopause.
Yep.
And that's 150-ish astronomical units.
Yep.
So that's the end, right? That's it for the solar system.
Well, no.
Okay. There's a pattern here.
Turns out there's more stuff out there.
Right.
So we have this thing called the Oort cloud. And it's kind of it's a sort of spherical part to it. It's got a disky part to it. But it's this sort of holding zone in some sense for all the things like comets that come to us.
Right, yeah, because comets we were talking before about this newly discovered goblin-y thing, which we will come back to in a minute, dear listener. But comets are not dissimilar in that they are on these incredibly eccentric orbits. They come in really, really close to the sun, but then they get flung enormous distances away. And it takes, most famous comet is arguably Halley's Comet, and it comes around every 87 years or something. And some of them are on much longer orbits than that.
Most of them, yeah.
They go out really, really far, and presumably way out into the Oort cloud and that kind of area as you were talking about.
Yeah, so it's quite mysterious, this Oort cloud, because it's really, really far away. It's impossible to see many of the individual objects that are there because, stars put out light, so we can see them very far away, but little lumps of rock don't. So
it does beg the question then, astronomically, how do you know it's there? Like, how do you see it? Are you just inferring it from the fact that every once in a while one of them comes whipping around past the sun? And you go, oh, there it is. Oh, so most of the time it must be way out there.
Yeah, that's a major part of what we do. And we also do some ensemble stuff, so we know that the gravitational influence of the Oort cloud as a whole does impact a little bit the outer parts of our solar system.
If you're looking at those outer planets and bits and pieces, you can figure out the gravitational effect of other stuff that you can't see based on the motion of the stuff that you can see.
Exactly.
Right.
Yeah,
okay.
Exactly.
Okay. So there's this Oort cloud.
So there's Oort cloud. Now, this is going to blow your mind a little bit.
Okay, I'm ready.
The Oort cloud is 5,000 to 100,000 astronomical units away.
Okay, that's a jump. So we've just gone from the heliopause being at roughly 150 to the Oort cloud, which is now in the thousands to the tens or even hundreds of thousands.
100,000.
That's nuts.
That's really rather big.
I'm starting to lose my grip. Starting to lose my grip on reality here, Emily. Help me out. So,
well, I can tell you how far it is to the nearest star.
Okay, all right. Nearest star?
268,000 astronomical units.
Hang on. So the Oort cloud goes almost halfway to the nearest
star.
Star?
Yep.
Really?
It's huge.
That's nuts. That has totally changed my concept of what the solar system is.
Yeah,
That's amazing.
Yeah, you think that where there's just little blip, and then there's just a lot of empty space, and then there's the next star with its little blips.
It turns out not so much. Reverse engineering that, though, I guess that's not. I mean, I can begin to make sense of that because, you said a second ago that the heliopause is where the influence of the sun's radiation stops and sort of melds into or gets taken over by the interstellar medium. Okay, I can see that. But if not the radiation, you're really talking about gravity. And so how far does the sun's gravity extend? Well, it extends in principle forever. It's just that eventually you're going to find something big and closer to you to be gravitationally attracted to. So it's not so surprising that say halfway between us and the nearest star, if there is some stuff flinging around on one side of that, it's going to go, I'm going to fall towards the sun. And on the other side of that, it's going to, I'm going to fall towards this other star.
It's got to go around something.
Yeah, I mean, the sun's influence really does extend all the way out there gravitationally. I just never really thought of it that way. That's nuts. Okay, so mind-boggling scale of the solar system end. Well done. Blown my mind. So let's now go back to this news story then. The Goblin. The Goblin, which we've seen 3 years ago, has been spotted. Lump of rock. It's not a planet. It's a dwarfy planety subclass of lump of rock thing. And those are technical terms. But it's on this enormous, crazy orbit. So now that we have the benefit of knowing what those milestones are in the solar system, where does the Goblin fit in?
So remember the Kuiper belt finished at 50 astronomical units.
Yep. So Neptune was at 30, Kuiper belt finishes at roughly 50, and then we've got the heliopause at 100 to 150.
Yep.
So where's the Goblin?
So it's in between. So it's 65 is what's called perihelion. That's its closest that it ever comes in to the sun.
That's its closest?
Yep.
And its furthest?
2,300.
So it's right out there in the Oort.
No, not quite
the Oort,
no. But, well,
it's out there. Yeah.
Definitions get a little fuzzy.
Splitting hairs, surely, at this point. Point is, it's a really long way away.
Really long way away.
Wow. So, okay.
That's
2 questions immediately.
So eccentric. In all forms of the word, right?
Good use of the word. So 2 questions immediately jump to mind. First of all, how did anyone see it? And second of all, no, the first one's completely taken over my head. So let's start with that, and the other one may come back to me. How was this even spotted?
So we have to, I cannot underestimate understate how incredibly difficult it is to find these things, right?
I mean, if this was a Jupiter-sized planet out twice as far away as Neptune, I'd go, no, fair enough. Okay, that would have been tricky, but well done. This isn't a Jupiter-sized planet. This isn't even a Mercury-sized planet. This is a lump of rock, Emily. How did they see it?
300 kilometers wide. I mean, 300 kilometers, that doesn't get you very far, right?
Yeah. You haven't answered my question yet.
Okay.
You're dodging this one.
No.
They're making it up, aren't they?
No, it's cool. It's very, very cool. So first of all, we start with surveys. And it turns out the surveys that we do to find new transient objects do pick up an awful lot of new things. And so we start with looking for something that's moving differently to the stars, and then we start to follow that thing up. And so this particular object was followed up by the 8-meter Subaru telescope, which is in Mauna Kea in Hawaii. And it's a fabulous instrument, and it's often used for this kind of work. In fact, it's one of the only telescopes in the world we can use to follow up these objects.
So when you say it's an 8-meter telescope, the primary mirror of this telescope is 8 meters across.
8 meters across.
Which is non-trivial. That's a good
size. That's a really big telescope.
Yeah.
It's one of the biggest in the world. So very, very cool. But what's really special about Subaru is that when you that's designed so that you can see a large chunk of the sky at any one time. That's really important when you're not 100% sure where your object is.
Yeah, let's not get too accurate because we may be looking in completely the wrong spot. So let's take a broader view. And we're looking for, are you looking for it directly at that point? Or are you looking for it passing in front of a distant star?
No. you can find with these super large telescopes, you can actually get just enough light to be able to see the reflected light from the sun off these objects.
From something that small, that far away.
That tiny. And the pictures are up on the website, so we have to backtrack a little bit. We haven't actually credited the wonderful scientist.
We should probably do that. Yeah,
it is. So, and was led by a guy Shepard at the Carnegie Institute of Science. And on their release for this object, when they put out the press release, you can actually see these lovely images and see this tiny little speck. And that's the Goblin.
Oh, props to astronomers. I mean, I know that's the whole point of this podcast. We wouldn't be doing this if it weren't, blowing your mind every week. But it still blows your mind that that's even vaguely possible. So well done all.
Yeah.
Fantastic. So the Goblin, this just absolutely bonkers orbit, which starts ludicrously far away and then just gets nonsensically far away. But it's also telling us something. It's telling us that it's potentially not alone. Well, we know it's not alone because you said that it's one of a group of similar kind of objects. So we've seen other things like this before.
Yeah. So we have some pretty weird and overlapping definitions for minor bodies, shall we say, in the solar system and beyond. So there's everything that's beyond the orbit of Neptune, that's what we call a minor planet, so a little thing. That basically comes with a definition of a trans-Neptunian object, or a TNO. And there's a group of these TNOs. So we know of several thousand, 2,000 maybe, maybe a few more of these TNOs. And there's a special sort of subgroup within them called the extreme TNOs, so ETNOs.
Like it.
So extreme TNOs have these really eccentric orbits, so of at least 150 astronomical units, really huge, wide orbits that could go, they're just all a bit crazy. And there's a few of them that we know about. So we know about Sedna's a very famous one. So you might have heard about Sedna in the last few years. There's another one that came out in 2012 that didn't get a fancy name. So we just have to call that one 2012 VP113.
Yeah, I can see kind of why with this one they went back to, let's call it the Goblin. Give these things names.
But there's another handful of these kind of objects. And they're all on not only these extreme kind of elliptical orbits, but they're all tilted in terms of the plane of our rest of our solar system,
like Pluto was. So all of the actual planets, as you said, in the same plane. Pluto and these what do you call it? Extreme TNOs are tilted up at an angle. All the same angle? Similar angles?
No, they're all sort of a bit all over the place. But if we come back to how we think our solar system formed, we think there was this kind of quite a big disk that was the leftover material from how our star formed. And that's why all of our planets are all in the same plane, because they formed out of this disk. Now, if you're going to have stuff that's then in an inclination or at an angle to that disk, something has to have happened, right? Something's perturbed those objects, or something's changed in the way that these objects have come about. So to do that, you need to do some really sophisticated models of the solar system and how it formed. And one way to do that for these extreme TNOs is actually to have this planet 9 sitting out there.
Right. So in order to make these objects, in order for the solar system to have these objects at these crazy angles with these crazy orbits, one possibility, you're saying, is, well, what if we throw in a 9th planet? Big honkin' thing out there even further that we haven't discovered. But if it was there, it would do this.
Yeah.
Yeah.
Yeah. Because we know that these extreme TNOs are not really affected by the other gravitational heavyweights, if you like, in our solar system, Jupiter and Saturn.
Why? Because they're just too far away.
They're just too far away.
Right. Yeah. So you can't explain their eccentricity with what we can see. So you've got to start throwing in things that we can't see. Yeah. So how strong is this from an evidence point of view then? Is this sort of pointing out saying, it's there, or is it, well, it might be?
Well, I really liked how one of the authors described it, and they said it was just basically breadcrumbs. We're picking up the little breadcrumbs, they're pointing in this direction, and we're going to have to find some more. So
this is not a sign to say, look, we should start sending... start preparing for the first mission out to go and visit Planet 9, because we're still not sure that it's there. but the evidence is starting to build.
Yeah. Actually, we do have some parameters that if it does exist, we sort of think it might look like this.
Okay. So if it did,
Yeah.
what is it?
So it's going to be a super Earth, as we said, a few tens of masses of the Earth, something like 2 to 4 times the diameter of Earth. So, pretty hefty thing.
So is there anything within the solar system at the moment that's comparable? I mean, there is a kind of a big gap, isn't there, between Earth and Venus and then the next biggest one? Which would be Neptune.
Yeah. So between Earth and Neptune, we don't have anything that size, but we see lots of these objects in other planetary systems. This is one of the great results from Kepler, was that we found all these super Earths or mini Neptunes or whatever you want to call them.
Right, yeah, all of these exoplanets around other stars, which are sort of sitting in that gap. So that gap's not there for any other reason than it just happens to be the way our solar system has formed.
Yeah.
But the thing that might be out there being planety-90 type thing is sitting in that range of 10-ish Earths.
Yep.
Okay.
So it will be on an orbit which is something like 150,000 years long. Now,
Yep.
to give you perspective, Pluto at its orbit of 30 to 50-ish astronomical units is 250 years.
250 years. And sorry, Planet 9's orbit would be
15,000.
Wow. Yeah.
That's
okay.
really going to be far away.
Yeah.
Really, really far away.
That's a long way. So if it is there, no wonder we haven't seen it.
Yeah.
Yeah, because it's a long way away. It would be very hard to see. And it also wouldn't have gone terribly far across the sky in the time that we would have been looking for it.
No, yeah, it would have to be on a very eccentric orbit for it to move very quickly in the sky. And that's not really sure either.
Which is, I mean, one of the things I was reading about with the Goblin is that we were incredibly lucky to see it at all, because it spends so much of its time, like it's already a very long way away, but it spends like 1% of its time, 1% of its orbit, close enough for us to actually be able to see it.
Yeah.
And the rest of the time, it's ludicrously far away, which suggests to me a couple of things. It suggests, A, we were really lucky to see it, but B, the fact that we did see it means there's actually probably a hell of a lot of these things.
Yeah.
Because you're either really lucky or, as you've mentioned on this podcast before, you look where there might be lots of things and see if you can see one of them.
So I think probably it's a bit of both. We're lucky to capture this one, but we think that there's maybe a million trans-Neptunian objects in our solar system. So in some senses, we should see some of them.
And that's what we are seeing. We are seeing some of them. So it's not that the Goblin in itself is this amazing, wow, what a special thing it is, but rather we've seen one or a few, several, a number of a much larger class of things which are telling us a bit about what's out there.
Yeah. And if we can find Planet 9, there's a huge amount of question as to how on earth did it get there? Because it really shouldn't have formed out there.
Now, why not? If the sun's gravity extends, as we said before, I mean, in principle, forever, in practice, I mean, at least half as far as the next star, then why not? Why couldn't you just have a big planet forming out there all that distance away? What's the issue?
I think the simple problem is there's just not enough stuff.
Right.
Out there.
I guess, yeah, okay. To make a planet, you need stuff.
Yeah.
Yeah.
And you need to have stuff in that disk when all the rest of the planets are forming, right? We don't have any planet formation mechanisms outside of star makes disk as it's being born. Planets come from disk, right?
So from the point of view of gravitational dynamics, there's nothing against having a big honkin' planet that far away, but from a evolution of the solar system point of view, that shouldn't have happened.
Which is very, very interesting then. How did it get there? What is it? There've already been lots of theories as to what Planet 9 could be if it does exist. And these actually apply to exoplanets as well. If we see weird rogue exoplanets orbiting out in these kinds of distance.
What are the leading contender theories?
So we've got kind of three. So you could have, maybe it was the core of an old gas giant, or a gas giant that sort of didn't quite get the gas, if you like. So something like Jupiter or Saturn that didn't quite get an atmosphere and then somehow got kind of kicked out to the outer parts of the solar system. So a very...
Details are a bit sketchy
young,
there.
but it was quite young when it was kicked out, let's say. Could have been captured. Now, the orbit will probably tell us quite a lot about the difference between those two theories. If it's kind of orbiting in a way that might have been kicked out, as opposed to a weird and wonderful orbit where it's been captured by our solar system. And we know that there are lots of rogue planets drifting around in our galaxy. We've seen them, and we've seen thousands of them in other galaxies. So
one of those sort of wandering and being deflected into a path which then gets captured within the sun's gravity. Not completely surprising.
Implausible, no. Or basically could have been scattered from having an outer orbit, so something round about Neptune, and then kind of interacted with something and got a little bit pushed out. Basically, it's just an ice giant that went a bit further. So
those three theories are all a little bit hazy on the details, but then that's not entirely surprising given that we don't even know this thing exists. So I'd say that's a fairly good start. And now, if we want to learn more about these kind of objects, so if we want to learn something about the goblin or find more goblins out there in the solar system, one of the things I came across that I thought, actually, that's really cool, is that this is the one of areas of astronomy where actually the public can really help out. Okay, a little bit of citizen science. Bit of citizen science. So there's actually 2 projects up on Zooniverse, which is kind of the hub for all citizen science. Check it out. It's a great place. We'll put links in the show notes, definitely. Yeah. If you haven't ever been there, you should. It's very, very cool. So there's 2 active projects that are looking at finding these kinds of objects in our solar system. There's one called Backyard Worlds, and that's using lots of different data to basically compare, can you find anything that's moving where it shouldn't be, things like that. And there's a similar one using quite new SkyMapper data. So SkyMapper is a little telescope in Australia that's been it's a robotic telescope that's been very, very dutifully observing the night sky every night. It just opens up, starts observing. Just doing its thing. It's not looking for glory or anything. It's just, this is my job. It's what I do. Here's my data. It's a very unassuming little telescope. It's gorgeous. I love SkyMapper. So the SkyMapper data, again, to have a look at, you can do kind of blink comparisons to see, there's the stars there. Oh, there's a new thing there. That's exciting. What's that? And actually, SkyMapper data got released in 2017, and they've already got 4 new candidates to follow up on for these kinds of objects. Great. So, if you want to get involved, I really, really, really encourage you to go and have a look at some of these links. Get on over to Zooniverse and find some new stuff. You could be responsible. You could help contribute to finding this mysterious Planet 9 in our solar system. And that's all we've got time for in this particular edition of Syzygy. We are produced, as ever, at the University of York, where Emily is an astronomer, and they allow us to use her office and give us a bit of encouragement to do this podcast every week. Emily, how can people get in touch with us if they want to? So we are on Twitter at SyzygyPod, and even after all these weeks, I think I can still spell Syzygy. That's SYZYGY. That's right. Pod. So at SyzygyPod on Twitter. We've got a Facebook page where we put up every single post and other stuff that comes our way that's of interest in the world of astronomy. We put up there as well. And Facebook, you just search for Syzygy Podcast. We'll turn up. You can find us. YouTube, we put up all the episodes on YouTube if you like to watch your podcasts. Sounds a bit strange, I know, but astronomy is a visual medium, right? And so every episode we dig out some of the pictures, the beautiful astronomical pictures that go with what we're talking about, that illustrate it, and we synchronize those with the audio and throw them up on YouTube as well. And of course, there's just our plain old vanilla flavored webpage, which is syzygy.fm. You can find all the show notes, all the past episodes, and all sorts of other information about
it
us
is anything but plain, let's just say.
Shucks. And listen, one other thing that I mentioned in our sort of interim summer podcast episode 17, which is that we have a Patreon page. So if you enjoy the show and you're thinking, I'd really love to help these guys do what they do, look, the number one way you can do that is just go and tell everyone you know about it. Because the more people who listen to us, as far as I'm concerned, job done, right? So go and tell your friends and family and say there's this cool thing that I'm listening to and you should too. That's the best thing you can do. If you're looking for more that you can do, then leave us a review, give us a rating, go to iTunes, go to Spotify, wherever you can find that will allow you to give us some stars and put in a few words in our favour. That's great. That helps other people to find us too.
And thank you to those people who have, because you've been so, so kind.
Oh, we've had some lovely, lovely comments. So thank you all to everyone who has. But if you're sitting there going, I still want to help out, then there is another way. And that is that you can help us out financially by becoming a patron on our Patreon page, patreon.com/syzygypod. You can go there and pledge us $1, £1, a month, even more if you really want to. And if enough people start helping us out, then that allows us to do bigger and better things with the podcast. It allows us to dream big, go and visit places, get people in, get exciting stuff happening. All sorts of possibilities there. So those are the ways that you can help us out. But we'll be back with another podcast again in a week or so's time. In the meantime, thank you very much for listening.
Thank you.
It's nice to be back from summer. We'll catch you next time.
See
Bye.
you.